We can use a calorimeter for many different things, and one of the most interesting and useful ones is to determine the heat capacity of something. This is actually the object of Lab 2 that you'll be doing, so this video might be very helpful for you as you prepare for that lab. Our learning goals will be how to use calorimetry to determine heat capacity for a sample that is an unknown sample. Now there's some strategies that we're going to use. Let me first remind you that a specific heat capacity is the heat capacity of 1 gram of a substance. So our strategy in all of this is going to be to measure the enthalpy change and the temperature change for an unknown sample of known mass. So we need to know how much it weighs first, but we're going to use other things to measure the enthalpy change, and we'll measure the temperature change for it in a separate way. So what we're going to do first is prepare a weighted sample and a calorimeter, and we're going to prepare them at different temperatures. And that's important because they're going to need to have different temperatures so that we can get all the information that we need out of this experiment. We're going to add the sample to the calorimeter. Now remember, they're at different temperatures, and then we're going to let them reach thermal equilibrium. Since they started at different temperatures, that means the temperature change for the sample and the temperature change for the calorimeter are actually going to be different delta T's. We're now going to relate the heat gained by the calorimeter to the heat lost by the sample. And once we do that, we can then evaluate the total heat capacity of the sample and simply divide by its mass to get its specific heat. So what does this look like? Let's imagine that we've got a mass here, and we've weighed it on a balance, and we're ready to begin our experiment. Well, the first thing we're going to do is we're going to put that sample into a hot water bath. And you'll notice that the temperature is pretty high in there. So the temperature of the hot water bath is at T hot. And we set the sample in there for a little while. It's going to equilibrate thermally with that. It's going to reach thermal equilibrium. It will then be at that temperature. Once it has reached that temperature, we're then going to move that hot sample into a cool calorimeter. The calorimeter has been prepared at a temperature of T cool. And once we've put it in there, we also are going to need to measure the mass of the water in the calorimeter so that we understand what the heat capacity of the calorimeter is. All right, now some time is going to pass, and after some time, both the sample and the calorimeter should be at thermal equilibrium, so they will have relaxed to a final temperature. That final temperature will be different from the T hot that the sample started with, and it'll also be different from the T cool that the calorimeter started at. So those three temperatures are related as follows. T hot is the hottest of the three temperatures, T cool is the coldest of the three temperatures, and T final, which represents the thermal equilibrium between the hot sample and the cool calorimeter, is somewhere in between. So let's use some real numbers and see how this works in principle. So what we want to do is we want to find the specific heat of a metal that has these details. It has a mass of 29.49 grams. It's heated up to a hot temperature of 354.7 Kelvin. The calorimeter is kept at a cool temperature of 296.3 Kelvin, and when the two of them reach thermal equilibrium, the temperature that's measured is 299.1 Kelvin. Now the other thing we're going to need to know is that the calorimeter contains 62.8 grams of water, which will enable us to calculate its heat capacity. Now, as an activity, what I'd like you to do is to pause the video and calculate the heat capacity of the calorimeter based on the information that you have here. You'll also need the specific heat of water. All right, hopefully you've had a chance to do that now. The calculation that you should have done involves the following. The heat capacity of the calorimeter would be the mass of the water times its specific heat. The mass is 62.8 grams. The specific heat of water is 4.184, so that would give us a heat capacity of 263 joules per Kelvin. I have another activity for you. Now let's find the enthalpy change for the calorimeter. So in other words, the calorimeter has increased in temperature from 296.3 to 299.1. You now know the heat capacity of the calorimeter. Find its enthalpy change. Okay, hopefully you've had a chance to do that now. You pause the video, I presume. And the calculation looks something like this. First of all, the delta T for the calorimeter is just the difference between 299.1 and 296.3, so it's 2.8 Kelvin. And the enthalpy change for the calorimeter is going to be its heat capacity times that temperature difference. So it's 263 joules per Kelvin times 2.8 Kelvin, or a total of 736 joules. All right, we're going to do the final part now, and that's to figure out the specific heat of our unknown sample. I'll remind you that its mass is 29.49, and the the enthalpy change of the calorimeter that we measured was 736 joules. So now, as a third activity, I want you to find the specific heat of the sample from this information. All right, hopefully you've had a chance to do that. The delta H of the sample is just going to be the negative of the delta H for the calorimeter. So it's going to be negative 736 joules, and it's going to be the mass of the sample times its specific heat times its temperature difference. Remember, it started out much hotter. It started at 354.7. Now we go from T final to T initial, so this is actually going to end up being a negative number. When we calculate all that out, we would find that the specific heat of this sample is going to be negative 736 joules divided by the mass of the sample, 29.49, divided by the temperature change for the sample, which was negative 55.6. And from all of that, we get a specific heat of 0.449 joules per gram Kelvin. Now you can use this, and you could look up things in a table and match this specific heat with other objects in the table. Since we know it's a metal, it's going to narrow down the possibilities. But based on this value, you would, I think, come to the conclusion that the sample is probably iron.